At the core of engineering, a lot of times I look at it as I have a physical problem and I need to solve. I got to get this aircraft in the air. I need it to go this fast. I need it to go this far. I need it to weigh less than this, and I need it to cost this number. At that point, I'm not really thinking about all the ConOps. As a chief engineer, you're really initially at least focused on what does this product look like? I think that's a place where actually some of the community outside the engineering community can come in and help the user, for example. Users are the best input to developing a product because they know what they need.
Welcome to The Vertical Space, the podcast at the intersection of technology and flight, featuring deep dives with innovators, early adopters, and industry leaders. We are your hosts, Jim Barry from Celerity 05 and Peter Shannon and Luka Tomjanovic from Radius Capital. At Celerity 05, we believe that breakthrough air transportation capabilities come from leveraging current and emerging technologies, and that companies achieve profitability through relevant technologies, strong teams, and a deep understanding of the aviation market. Connect with global aviation experts at celerity05.com for feedback and recommendations to chart your path to success. At Radius Capital, we invest in early-stage deep tech that redefines what is possible in aerospace. We partner with founders building next-generation aerospace capabilities, from advanced design and development tools to the digital transformation of the flight environment, novel use cases and forms of flight, and the software and systems that make them possible. If this describes you, reach out. We're excited to connect. All right, let's dive in.
Hey, welcome back to The Vertical Space and a conversation with Carey Cannon, retired senior chief engineer after a 38-year career at Bell Helicopter. So yes, many of you are thinking the same thing we were, how great it is to discuss the realities of vertical lift with someone who has been a chief engineer of a premier helicopter company, and to understand the realities of building and deploying helicopters and think about how the lessons learned apply to the slowly emerging world of eVTOLs. Carey starts out mentioning that you can't underestimate the time and money it takes to deploy vertical aircraft. He mentions that today eVTOL manufacturers are underestimating the time and money it will take to deploy their aircraft. I really liked his comments that getting in the air is actually the easy part. It's cool listening to why and how Carey entered aviation and vertical lift, and how he went from being a car guy to getting into helicopters, and how he wanted to soak up all things helicopter. We discussed the engineering lessons from helicopter development, including unmanned aircraft, and the programs Carey was involved in, and why some were more memorable than others. You'll love his discussion of some of the lessons learned from those projects. He also discusses the technology gaps that existed along the way, and how he and Bell addressed those gaps. We then have a discussion of the fundamental principles of helicopter design that remain unchanged. We discuss the enduring lessons he learned from helicopter development, and he discusses how a lot has changed and that nothing has changed. He discusses the challenges of energy storage and how it's the most pivotal piece of technology for the eVTOL space. Carey then discusses some of the biggest technical, operational, and commercial implementation hurdles eVTOLs must overcome to be successful. And you get to hear some of Carey's perspectives on what he thinks are some of the headwinds and tailwinds that eVTOLs may face. Next is an important conversation on why helicopter OEMs are generally standing on the sidelines when it comes to eVTOL development, and that there's a business case that has to be made, and why some of the OEMs may just decide to wait it out for a while. I really liked his comment that many of our guests have echoed, that it's easy to lose sight of the entire picture of what the true ecosystem is for these platforms. Towards the end, he discusses the role and his perspective of the startups. He mentions that few will survive the people-moving part of electrification. By way of background, Carey is a retired senior chief engineer after a 38-year career at Bell Helicopter. His roles included chief engineer of the U.S. Army Future Long-Range Assault Aircraft, chief engineer of Bell Innovation, chief engineer of the Bell 505 Jet Ranger, and the Bell chief engineer of the U.S. Navy MQ-8C Fire Scout. Chock full of the realities of vertical flight. Our many thanks to Carey, and to our guests. We hope you enjoy our talk with Carey Cannon as you profitably innovate in the vertical space.
This episode of the Vertical Space podcast is brought to you by UAvionics. UAvionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let UAvionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. UAvionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace. Carey, real pleasure to have you on the Vertical Space.
Hey, so thank you so much for inviting me. This is an honor and looking forward to it.
Likewise. So we usually start by asking if there's anything that very few in the industry agree with you on. And based on your vast experience, I'm sure there's more than just one thing.
As I think about that, I don't know that there's anything major that the broader audience wouldn't agree with me on. I think there is obviously there I have some insight to how much energy, and I don't mean electrical energy, I mean how much time you have to put into doing these designs, certifying these designs, and the complexity. And and then on top of that is the sort of the financial piece of this. It's crucial that people understand what the commitment takes to be in, aviation design, whether it's eVTOL or conventional helicopters.
What about this do you think is least well understood?
How much time and money it takes. The technology is there or close to there. I mean, obviously there's areas where we need to improve. The batteries have got to get better, for example, for eVTOL, but it it just takes you cannot underestimate the amount of time and money that it takes to develop a platform, whether that's conventional helicopter or eVTOL.
I think there's a general rule for building large commercial aircraft, blank sheet designs, that it's roughly 10 years, 10 billion. What's a rule of thumb for developing a modern helicopter?
So it's a pretty wide range because in some cases you have derivatives, and I think those can probably be developed for sub $1 billion. And then you have something like a Bell 525 fly-by-wire, state-of-the-art everything. That's going to be in my opinion, the multiple billions of dollars, I would believe. And so wider range probably, but still that's a lot of money.
So I know we're going to talk a little bit about eVTOL later. When you talk about it's just really expensive to build helicopters. As you look at the cost estimates for some of the bigger eVTOL companies, what's your first impression, given how much you know it costs to build a helicopter? Is your initial impression that they're underestimating the cost and effort to build something that goes vertical?
Oh, absolutely. And I've actually, made a few comments as I sort of track the eVTOL landscape, like on LinkedIn. It's a balancing act all the time. You have the people who are financing it, and you have the designers, and you have the salesmen. And it's this balancing act of I can get this product finished in this time frame, and then you base your business model on that. And that business model obviously includes the financial piece of it and what's going to be the return on investment. And it is underestimated every time because you have the salesman. You need to have first flight, for example. You know, you there's a lot of pressure on the design team, flight test team to get to a first flight because that's a milestone. It always takes longer than you want it to. And it's just a series of those types of milestones as they string out, and everybody wants it to happen faster. And quite frankly, sometimes flying is the easy part, getting it in the air. But when you really look at the complete picture of this has to be designed, flown, certified, safety, noise, all of these elements that each take dedicated tests and retest and redesign. That's where I think the two paths depart a little bit from a financial standpoint. And I was around when this all was just getting started, and we were all saying, hey, we this needs to be this 5 to 8 year sort of cycle, and these will be all over the sky. Well, fast forward 15 years, and you can see where we're at. There's a there's a lot of folks that are getting closer. I'm not sure how close they are to the full product, the full certified production line, continued airworthiness, and just air traffic management of those vehicles. So that's sort of it in a nutshell.
So, Carey, from an engineering organization standpoint, what are the key attributes of a successful engineering organization, for instance, in rotorcraft, where you have your experience? And then help us think about the question of startups versus established companies going into this VTOL challenge, whether it's eVTOL, but these new aircraft. What are the hurdles that the large company faces in succeeding in this new effort? And what are the hurdles that a startup that has to form the team from the ground up faces?
Yeah, so that's a very very interesting question, and can go pretty deep pretty quickly. I think when you at the highest level, when you look at an established OEM, there are processes and procedures that are in place, and I'm not going to say it's a cookie cutter, but there is a plan that's put together, an organization that is established. That organization usually reflects the bigger picture of the organization of that OEM, and then you put that against the startup, who usually has a small team, usually very bright engineers, don't know what they don't know, and that's not necessarily a bad thing, because then they can be a little more diverse, go a little faster. Some of the processes don't slow you down, and that's on the front end of this. The back end, those processes is what makes it all happen. So as a startup, at some point you have to start inserting some of these processes, some of the rigor, understanding the entire path to production, which is not what you're looking at when you're saying, I have this concept for a vehicle, this is going to be its configuration, these are the technologies that are going to enable me to do it, and I need to get it in the air. So I think that's at a high level, that's sort of the differences as we look at established OEM versus, hey, some group of really smart engineers that pull themselves together and say, hey, I have an idea.
Let's rewind and zoom out a little bit. How did you start in aviation? What originally drew you to engineering and helicopter engineering?
So my path was pretty interesting. I grew up out in the country. Didn't have a lot of exposure to aviation. It was always, I always had an interest in it, but I didn't get any hands-on direct exposure. I jumped into college as an electrical engineer. Didn't really know what I wanted to do. I wanted to graduate college and get out, and it was. I'm not going to say it's by accident. I've had a very blessed career, but I started running around with some car guys that were engineers, and they were engineers at Bell. And they were like, hey, have you had any interest in helicopters? And so, literally, that was the start of my career. I sent a resume in and got an interview, and that interview was so eye-opening, because I got to interview with a lot of different groups that would use electrical engineers, for example, and I had no idea of all of the different elements. And so from that point on, you know I jumped in and just wanted to soak up everything there was about a helicopter. And I was very naive. Didn't understand it all, but it was obviously it sparked my interest, and it was something that I had a passion for. Once I got into it, it wasn't one of those things where you have a passion and you follow it. Mine was kind of inverted from that, and I feel blessed because of it.
What is it about helicopters that captured you? Is it the complexity? Is it the challenges with engineering them? Is it something else?
Yeah, it's a mixture of all of those things. The the capability that it gives you is, and flying in a helicopter is, just an awesome experience. What it allows you to do, you can't wrap your head around it till you've actually been in a helicopter, and you've been in it with a pilot that is very capable. I've flown a lot over the past 38 years, but I still enjoy, getting into an aircraft, whether it's just a joyride or a flight test card. I just can't say how exciting, the excitement is still there today.
And so 38 years later, you retire from Bell as a senior chief engineer. You were a chief engineer on multiple programs. Which stand out as the most memorable?
Man, that's a hard question because I felt like every one of them was just a step to the next. I think, I ended my career at Bell with the Future Long Range Assault Aircraft, the V280, Bell's V280, which is the Black Hawk replacement. That's a big deal. And that aircraft, tilt rotor aircraft, is going to give the warfighter something they've never had in terms of speed and reach, how long they can fly out. So I would say, obviously, that's something I'm pretty proud of, to be part of that team that worked on the proposal, that did the flight, some of the flight tests with the prototype. I didn't join the program. That aircraft was already developed, but just still being able to go out to flight test and watch it fly and see its capabilities. That's something that I'm really proud to be a part of, to say, hey, I had a small piece of that. It's the production aircraft's not built yet, but I have high expectations of what that team and the U.S. Army is going to do to give the warfighter that next piece of technology.
Line it up next to the Osprey. Give us a quick comparison, if you could, especially as it relates to the mission, to the warfighter. What are the principal differences? And of course, talk to safety as well, if you could.
Yeah, so at a high level, you want to continue to improve on safety. It has to be affordable. And so the way the manufacturing processes to the V280 is something completely different than it was back in the V22. You do things that make it easier to produce, more reliable, and I guess equalizing the dollars, less expensive to procure and maintain. At a high, you are still getting, from a performance standpoint, the twice as fast, twice as far sort of thing that you get in a V22. It's smaller than a V22, but I think it has a little more maneuverability. But the big things is, it has to be easier to build and maintain than a V22. The V22 was developed in the 80s. And you think about the technology, that was my first project to be a part of at Bell. And a lot of technology has occurred since then. So it gives the designer, a bigger palette of things to choose from, and materials, and analysis, and quite frankly, the flight testing of the V22 is going to educate the team on the V280. There is still lessons being learned from the V22 as it, is rolled into the V280.
How much of your work at Bell was developing to the requirements that the services handed out to you and the capital that came with it, as opposed to having a vision of what the demand is, what the unfulfilled need is, and then building something for the warfighter to then adopt?
So I think, with the V280, it's probably sort of a mixture. I mean, obviously the customer has a set of requirements, and it's the job as OEM to meet those requirements. And as you could see from the competitors, the shape and technology for that program was vastly different between the competitors, and and that balancing act of requirements and capabilities and things that a given platform can offer, that's an ongoing tug of war sometimes, to sort of weigh, hey, here's what the requirements are, here's what we could, maybe we could, if that requirement wasn't quite so stringent, we could provide a lot more capability in this other area. And so it's a constant, communication discussion. I'll call it a discussion. Sometimes it's more of an argument, but with the customer, to say, here's the art of the possible. And as you move into things like tilt rotors, and you think about the U.S. Army, for example, that's not a paradigm that they've lived in. You need input from the Navy and the Marine Corps into U.S. Army to say, here's what this can do for you, and maybe some things your ConOps will need to change, and that's really important because that might tailor your requirements somewhat.
What about some of the research vehicles, some of the technology demonstrators that you worked on that never made it to production, but were probably a source of great learnings?
Well, for me personally, I was a part of a very small team that back in the early to mid 90s, we developed a little tilt rotor unmanned aircraft called EagleEye. It actually started out as a DARPA paper design where we wrote a proposal to DARPA, and it started out as a paper, then we came up with enough money to do a demonstrator, and that program, which turned on and off a few times, but was a big part of my career. 10 years of my career was working on that EagleEye. And you think about the technologies that we had in the mid 90s and the budget we had of trying to build an unmanned aircraft that ultimately flew over 200 knots. It was vertical takeoff, fly by wire. It weighed approximately 3,000 pounds in its prototype form, and to demonstrate to a customer, primarily the Navy at the time, the capabilities that a tilt rotor UAV could give you, and all of the learning in my career. I hadn't even been an engineer for 10 years, and the exposure that you get when you're on a small team like that, where everybody's got to do things that they're not the expert in. If you've only got 10 to 20 engineers and you have a whole platform that has to be designed, built, flight tested, it certainly helped round my career and gave me an appreciation for all of the other things that go on in a flying platform. And obviously, data links in the 90s and GPS in the 90s wasn't the greatest. And so just to fly that aircraft on a regular basis, in the desert, or we even flew it at Pax River, was pretty amazing, and exposed me to the big picture of aerospace, and truly being on the front edge of unmanned technology. Quite frankly, there were not very many platforms flying unmanned in 1998 with the technology we had, and so that was a really proud moment for me, and really gave me a foundation and an appreciation for everything that has to happen for an aircraft to be successful, whether it's successful financially or programmatically. But there's a lot of pride in the flying of that aircraft.
So, Carey, back in those years in the late 90s, what was your assessment of the state of technologies to ultimately make unmanned helicopters a reality? And, what did you expect in terms of timelines when those kinds of helicopters would be operational? How did that match up with reality?
So I think you're always optimistic. You want an optimistic timeline of how long it's going to take to develop, how long it's going to take to fly, what are going to be the problems. The reality was in the 90s was probably 2x of what we wanted. When you think about in the mid 90s, GPS wasn't available for everyone. There was selective availability, and all of a sudden, positioning was not as easy as it is today. Inertial systems. You think about the inertial systems that we had to put on this platform, it had to keep itself upright. Those control laws that were required to keep that aircraft flying, it wasn't the person on the ground that was going to be able to be keeping the aircraft upright. The person on the ground was just saying, I would like you to go in this direction. And when you think about the inertial systems of those days, I want to say that we had 2 GPS aided inertial boxes that was probably cost nearly $250,000 for 2 boxes. And at the time they were state of the art. They were ring laser gyros. But I think today your phone probably has almost the same capability as those boxes did. And that can just give you an idea of taking something that's the size of two or three shoe boxes stacked on each other now to a chip.
How did those lessons carry over to the Fire Scout? I think you were involved with the Fire Scout as well.
Yeah, so the Fire Scout is very interesting. Fire Scout was one of those bittersweet moments for me as an engineer. We used EagleEye in that competition for the Navy Fire Scout program. We were not chosen, and a paper design was chosen, quite frankly. We were actually in Yuma, Arizona, flying auto lands with EagleEye when the announcement was made that we were not selected. Now, fast forward 10 years, and Northrop Grumman approached, who did win, the Fire Scout, approached us and said, we need a little more capability. And we've looked at everything that's available to us, and would you be interested in sort of partnering with us to build a demonstrator? And we use the Bell 407 as the platform. So that was sort of the genesis of Fire Scout. We called it FireX at the time, where we took a manned helicopter and changed the fuel system, put some of the Northrop Grumman's avionics and flight control computer and data link systems in and adapted it to a 407. And then as sort of a joint team of Northrop and Bell went out to the desert and started flying a Bell 407 unmanned. That was used to the Navy to say, hey, here's something that could, sort of expand the legs and the capabilities of what was at the time MQ-8B, which was a Schweitzer platform, had started out as a Schweitzer platform, to give it a lot more capability. And so that was sort of the genesis of the MQ-8C, which we at that point then became a sub to Northrop Grumman, providing the platform, modifying the fuel system, making sure that you could put the sight on the aircraft, and something that I was really proud of. And it was a great relationship, I would say, technically, of merging the Northrop Grumman engineering and the Bell engineering together to build a platform, a helicopter that had more than 10 hours of endurance. That's a long time to keep a 6,000-pound aircraft in the air, and gives you quite a bit of capability, including the vertical lift from a Navy ship.
What was the pilot interface, the ground control station for the EagleEye and the Fire Scout? What did that look like?
So for the EagleEye, it was primarily just some off-the-shelf pieces that we sort of put together. We initially started out with an Israeli aircraft Hunter prototype data control center, and did its early flying with that, and recognized that that technology was too outdated even at the time. And we recognized that we needed a new ground control station. And the ground control stations in 1998, there weren't very many to pick from. And we went out and surveyed all of them and decided to basically do our own. And so that's where we just pulled together a team to build a ground control station, understanding that ultimately, for government programs, obviously we've got to come up with a common control station. And they've got a couple of different variations of that now, but this all predates that and basically showed the need for it. The STANAGs that were created to sort of standardize what the message structure and those kind of things. That was all being initiated as we were flying the EagleEye.
What was the actual interface? Was it some kind of simplified controls, or was it dropping pins on a map and the aircraft autonomously executed the mission? So what
Yeah.
was that like? And what was the level of autonomy? And what was some of the most difficult aspects of operationalizing the concept?
Yeah, so in an aircraft like a tilt rotor, the aircraft's going to have to keep itself upright. The control laws are going to have to be in place such that from a ground control station, you're basically not telling where every control surface should be. You're telling it, I need you to go this direction. The control laws will then dictate, hey, I need to go this direction, this fast. What needs to happen for do that? For example, nacelle angle. If you needed a slow speed, well, you weren't going to have to. You were not going to be able to be in airplane mode. So in the early days, we did have, I would say very simplified waypoints, and we could fly that aircraft to waypoints. And the I will say advent of a mission plan, which is basically what you get into today with a lot of unmanned aircraft, at least on the military side, where you put a mission plan in. You can modify the mission plan as you go, but the mission plan includes everything. It includes your altitude profile, speed profile, where you're going. That was the next step in say what we were doing with EagleEye at the time, but that was that wasn't really a piece of technology. That was just, hey, I need time to code this up, and wasn't really required for flight testing. And now you have very advanced mission planning tools, and you can pre-fly the mission in simulation and all of those things, which we're just getting started as we were developing EagleEye.
What was the biggest technology gap at the time? Was it the autonomous behaviors themselves? Was it the availability of the sensors, the command and control links?
Yeah, I think for us it was the data links. We were trying to maintain line of sight data links because we needed not only the command and control of the aircraft, but we were very interested in seeing what the telemetry was looking like coming back. How was the system behaving? Was anything shaking, or did we have any abnormal vibration? What are the temperatures and stresses? So for us, I think it was primarily the biggest piece of technology that could have helped us at the time was data link technology, and then I would probably revert back to the inertial systems that were available to us at the time.
What's your assessment of the state of the art of these technologies today? Are we still trying to close the gap?
I don't know, because with today, at least on the military side, you can put the mission plan in. Obviously, beyond line of sight is key. You have to be able to operate these aircraft beyond line of sight. So with a combination of, preloaded mission planning and satellite communications, there's a lot you can do with these aircraft that you couldn't do with the simple line of sight system that said, we're flying along, and the basic physics of RF that says you need to be this high if you're going to be this far away, and you're going to need this much energy, and then all of that gets sort of mashed together when you say how much bandwidth you need. How much data am I going to have to push up or push down? Obviously, the quality of a video downlink in 1998, some of the compression techniques and stuff that we know today didn't exist. And I think all of those things is what leads us to the technology we have today. That need to pack in a lot of data in a small bandwidth is, those are the things that have happened throughout history that drive the technology, quite frankly.
Looking across the programs that you worked on your career, what are the enduring lessons that the community has learned about rotorcraft and how to take this technology as it was maturing and really wrestle it to the ground, scale it up to what it is today? What does that look like in tilt rotor VTOL aircraft? And what does this likely look like as we go ahead into electric VTOL aircraft, or broadly aircraft with distributed electric propulsion, of which we know there are lots of different configurations that are not necessarily tilt rotors at all. Some interesting things about aviation is that a lot of the lessons are really enduring over decades and they don't change. And yet the underlying technology, the fabric in which we are doing the work, the manufacturing processes, the particulars of the propulsion technology, those are changing a lot. And the intersection between the things that endure and the things that are changing is really interesting. What are your thoughts in that area?
Okay, I'll try to untangle that a little bit. That's a pretty complex question. And I'll start by first saying physics hasn't changed. Okay, when you get down to the basics of physics, that is unchanged. Now, the way we tackle some of those physics problems has, and technology has enabled that. Technology in the form of materials, technology in the form of analytical tools and simulation that help us improve in areas. And I'll start out with saying noise, for example. You know, being able to do analysis on, rotor tip vortices and things like that, stuff that didn't exist 30 years ago of the tools we have today. So, can we make an aircraft today quieter? Absolutely. Both from the rotor, the engine manufacturers, and in a non-electric aircraft, they're doing a lot of work on how do they get their noise down, although that's a pretty big challenge because that's just by nature, you're going to be generating quite a bit of noise. So I think the the basics of flight, have not really changed. It's really how are we going to take elements or sub-elements of all of those things, take the technology of today, use the tools, for example, to put together a platform that is optimized. Weight is kind of like, noise. We all want things to be lighter because at the end of the day, we want more load carrying capability. And that's only going to be improved with, material technologies. I would say some of the analytical tools that allow us to make parts a little leaner than they once were. So to me, those are from a big picture, a lot has changed and nothing has changed. I mean, like the physics are there. As we move into eVTOL, we all know the challenges with, electric energy storage. That is not, in my opinion, where it needs to be yet. It's, greatly improved over 10 years ago. But when you actually want to take some of these things and put them into production, put them into use, build thousands of them, that's where that technology has got to continue to help us. And it's going to take things like battery chemistry and, AI and some of the machine learning, and some of those technologies may only be used in the manufacturing process. We may not be ready to throw in AI from a control system standpoint and how we would regulate something like that. But it's certainly a fantastic tool to use on something as simple as a CNC machine that's building rotor blade parts and can look at, hey, I know how fast this tool wears as I'm doing high speed machining, and I can make the adjustment on the fly, and I don't have to stop and have somebody put a mic on it. Those are the kind of things that are maybe a little bit smaller steps, but sort of the sum of all of it equals major shifts in the technology as we start to build some of these platforms. Does that answer your question in a roundabout way?
Yeah, I think it does. I mean, if there were a couple of enabling technologies that were markedly improved from where they are today, in your mind, what would be the technologies that would make the most difference in developing these platforms? Is it better energy storage for electricity? Is it something else in propulsion, like more choices in hybrid propulsion systems? Is it something elsewhere in the platform design?
Well, I personally believe the number one is energy storage. I think, and I want to say that's the all-encompassing of energy storage, not just the watt hours per kilogram. It is, charge rate, discharge rate, temperature. How does the battery operate over temperature? What's the life of the battery going to be? What's the infrastructure going to look like that charges the battery? So there's a lot of elements to energy storage, and not the least of which is safety. And how are we going to package this energy storage? Because that ends up in the watt hour per kilogram. And from Carey's perspective, is energy storage has to include the encasement of the cells, for example, that comes with that. So in my mind, that is the most pivotal piece of technology for the eVTOL space.
How do the services think about electrification of helicopters?
I haven't had a lot of conversation with the services on that, other than maybe the logistics piece. I think they're open to understanding and doing testing and research on, resupply platforms, not so much the people carrying piece, but the logistics side of it. And I think in my opinion, they're using that as the starting point to this path of electric vehicles. Is it probably looks more in the form of surveillance drones or logistics resupply, those kind of things, before you get into the bigger picture of actually moving personnel with an electric vehicle.
And why the logistics resupply, Carey? What's the principal value of the electrification?
I think there it probably looks at things like what's the foot, it's a relatively small footprint, although you've got to figure out how if you're going to send a drone to a forward operating base, it either has to have enough energy to get itself back, or there has to be some charging capability there. But I think it can be quiet. It can be not need roads or bigger aircraft. And in some of these missions, it's not like you're needing to relocate an armored vehicle. You need batteries, MRE, water, those types of things. And I think that's a really interesting thing to look at from the services standpoint, and especially I think some of the what you're seeing coming out of Ukraine and that conflict is starting to maybe open up a whole new line of ConOps for electric platforms.
Explain how power capabilities and requirements have changed over the last 30, 40 years for helicopters, military or commercial. What have been the biggest changes?
So I think on a lot of the hydrocarbon engine platforms, obviously moving to FADEC controlled engines and health monitoring, that has been a huge step improvement to the propulsion systems that I've seen, over the past 30 years, as the engines are not only, the efficiency is increased, but the reliability and the health monitoring piece. I think the health monitoring piece is, and I say this in a broader sense than just the propulsion system, but health monitoring in general is one of the next things that we're really getting into now, to understand, hey, we can preventatively replace a part, a bearing, a rotor blade, because we see what's happening and it's going to fail in the future, and get it replaced ahead of time. And so I think things like that are the biggest changes that I've seen in the propulsion side of things. I guess the materials are also playing a part into that. As you look at some of the modern turbine engines, for example, they are in some ways simpler than, especially as we move to electronic control things, where we don't have a bunch of mechanical linkages and guide vane linkage, those kind of things. It has certainly made a step improvement in the propulsion. And that even includes emissions.
As you look at the electrification of the helicopter and the needs going forward, commercial and military, and you see that the eVTOL has outlined different areas where they may be able to provide value, are you a little surprised that, I mean, at the end of the day, you are the helicopter experts. Are you a little surprised that the electrification has introduced new use cases where an awful lot of guests we've had on this podcast have said, I think of these things as helicopters and they happen to be electrified or there be a hybrid propulsion? Are you a little surprised by this opening up of new use cases where that was a Bell use cases all along? It just happens to be with electric power. What are your thoughts on that?
Yeah, I think part of it is the scalability. The electrification does provide, I will say, the ease of scalability is maybe a better way to put that. And we develop products, and I mean, it's been my experience over the years. We focus on, building a product that'll go this fast, this far, be this maneuverable, and we don't even think about some of the ConOps, if you will, for that. And then we start flying it, and we recognize, oh, do you realize we can do this, or we can change this? And maybe we were thinking about moving people, and you recognize that you know a better first step may be to move stuff, and a little bit of crawl, walk, run at the same time, But at the core of engineering, a lot of times I look at it as I have a physical problem and I need to solve. I got to get this aircraft in the air. I need it to go this fast. I need it to go this far. I need it to weigh less than this, and I need it to cost this number. At that point, I'm not really thinking about all the ConOps. As a chief engineer, you're really initially at least focused on what does this product look like? I think that's a place where actually some of the community outside the engineering community can come in and help the user, for example. Users are the best input to developing a product because they know what they need, whether that's in a military application or commercial application. What is it that we need to provide you that will make this platform useful? And I think that that's kind of been a refreshing and eye-opening thing at Bell and likely the other OEMs as they start looking at getting customer feedback, involving the customer on the front end, not the back end. That was one of the things that, the 505 I think did really well was having that customer advisory group to come in there and say, what are the things that need to be improved for a platform of this size and this capability? And so at the end of the day, I think that's where this all has to sort of culminate in providing capability and quite frankly, sort of taking your blinders off to what's the art of the possible with the platform. And as OEM, we didn't always do that very well.
On that note, have you experienced or come close to experiencing anything similar to an innovator's dilemma while you were at Bell? And the argument goes that the incumbents focus on sustaining innovations and incremental improvements that built on their legacy products and that serve their existing customers. And it's a very rational thing to do for a large company. While disruptive innovations, they start as inferior niche markets and then ultimately overtake, large portions of the market. And so that's how it played out with Kodak and digital photography and, Blockbuster versus Netflix and many other examples. What are the parallels to that if you look at this next wave of innovation in flight? And have you, over the course of your 38 years at Bell, ever gotten to that situation where you are kind of seeing the future and saying, okay, well, we're being the Kodak here?
Yeah, so I think that's a I'm going to call it sort of an easy trap to fall in. I think I was very fortunate because of a high percentage of my career was more on the research or development side of things. And one of our sort of mantras of the innovation group was fail fast. Where we didn't have the I will say the OEM mindset at least for thinking about what's the art of the possible for a different vehicle, whether it be electric, whether it have a fuel engine, or whether it was just a piece of technology for vibration dampening. I think at the higher corporate level that there's always pressure to utilize what you have. Let's just improve on what we have. Part of that is, quite frankly, just the financial and return on investment for starting a platform from scratch is a very expensive endeavor. And as an engineer, you can't turn a blind eye to how much money it's going to cost. What is this project going to do? Now, we would all love to do that. We'd all love to go, hey, I'm going to go out in my shop and I'm going to, we're going to take however long it takes to develop a platform that has this capability. But at the end of the day, there are always people that you have to look at it as, hey, I need a platform. How much money is it going to take to invest in it? So it is refreshing some of these startups that I will say don't have that mindset, at least on the front end. And I think it allows for more innovation. Now, some of it you may not be able to put to use or take the time that it's going to take to mature it, but it's the starting point. All things aviation are building blocks across the board. Those are the things that drive the technology, whether it's in materials, whether it's in computer software or engineering tools that make it happen. It's all building blocks. And We all stand on the, you know, the heritage and the shoulders of the generations that started this, and we've just, continued to the evolution, and the people who do that faster and for less money are the ones that are successful.
Why do you think that many of the large incumbent OEMs are standing on the sidelines as it relates to eVTOLs? And most of the industry is being pushed by, startups that obviously have this existential need to get things across the finish line. Why aren't OEMs going in more vigorously?
I think there's just a caution there of understanding the commitment that it's going to take and the state of the technology. And 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 I will say for eVTOL, it's the state of the regulatory side of it is not something to be ignored, and that including airspace management and those types of things. If you are going to, flood the skies with these vehicles, you're going to have to rethink how you do airspace management. But at the end of the day, I think for the OEMs, and this is just Carey's opinion, there's this business case that you have to convince the executives and stockholders that there's a business plan here, because I mean, let's face it, if you're going to keep the lights on, you have to still continue to make some money. And if you already have a, let's say, a large portfolio of platforms, they can't sit still. You're going to constantly, I mean, your car, every year, there's some tweaks made in an automobile year model. That takes funding. And so when you look at the OEMs who have to slice the pie up in a lot of different directions, the financial pie that is, I think that's one of the things that says maybe we just wait a little while and let's get the regulatory side of it sorted out, and let's get the technology where it really needs to be. And yes, maybe we're not on the headlines of the first passenger carrying commercial available air taxi, for example, but that's not necessarily bad.
It's an expensive headline.
Yes, it's a
Even if,
very expensive headline.
even if you're on the revenue side, even if your forecasts were the same for the next 20 years, if you lined yours up versus some of the bigger innovators in eVTOL, your understanding of the cost and the risks are probably far greater. And your understanding of certification, your understanding of integration, your understanding of what a vertical lift aircraft is going to be capable of doing and not capable of doing is probably far different. And so the estimations of profitability were probably far different on your pro forma versus the others. What are your thoughts on that?
Yeah, so I've had people ask me in the past, "Hey, you're the chief engineer of this project or that project." And being a chief engineer, for example, is not all technical. There is a financial piece, there is a planning piece, and I will say, at times has to temper my enthusiasm as much as I would like to go tackle a technical job. The reality is there's a finite amount of money. And typically as an engineer or an engineer leader, you have to write a plan that says this is how I'm going to get from point A to point B. This is how much money I think it's going to cost. And then the negotiation starts with, well, this is how much you think it's going to cost, but this is how much money I have. And as you go through the cycle, and how much management reserve do we have, for example, and you start making decisions based on that. And I do think, and this, I would say only comes with a few decades of learning, is it's really expensive, and we're all optimists. I think the salesmen are optimists, the investors are optimistic, the engineers are optimistic, and that's a fine balance of the technical versus the financial versus the schedule. And schedule and financial are kind of one and the same, because the longer it takes, the more money you're spending. And so yeah, I think I certainly have an appreciation for how long some of these take, and the bigger picture of, hey, it's not just the technical aircraft, it's what is the ecosystem that's going to make this work. The manufacturing side, the continued airworthiness side, the maintenance side. You know, it's you certify an air vehicle, well, you have to also get a production certification on the plant that's building it. And are there policies and procedures in place that the regulators are going to go, yes, I think those are things that on the surface you don't think about when you're just saying, hey, I want this platform to lift 1,000 pounds and go this fast. And I think it's easy to lose sight of the entire picture of what the true ecosystem is for these platforms. And for example, and it's always been not a pet peeve, but I look at people that are laying out heliports or vertiports. And there's some great artist concepts of, stuff that you might see in Star Wars almost. And then I think about the reality of, these multiple pads, the interactions with aircraft to aircraft, the prevailing winds, and the power margins that these aircraft are they going to be able to overcome that? You can put a vertiport hanging off the side of a building, but depending on where the prevailing winds are, you may not be able to land and take off that aircraft. And I think those are the kind of things that all of a sudden, that's where the rubber hits the road, the reality of an aircraft system that is often lost when you're just doing the basic design.
What do you think about the idea that people talk about, that maybe the way to thread the needle is to pursue the innovation of these technologies in physically smaller platforms rather than developing a 5,000-pound gross weight aircraft? A company can go a lot faster and they can do it with less capital if they're developing something much smaller, like a 300-pound gross weight aircraft, because within that, some of the critical technologies are common. How do you look at that? I mean, you've had some experience working on aircraft that are smaller as well. And what does that look like?
So I think there's probably some value in thinking along those lines. I certainly think it simplifies the big problems. It simplifies what the infrastructure needs to look at to support the platform. It probably supports the where are you going to operate the platform and what is its mission.
Does it let you iterate faster?
It can. It can also sort of expose at the smaller scales, sometimes a small technology advancement can be the difference. Just a little bit more battery capability, or the, we'll say, charging infrastructure required for a smaller platform. It's common. We can find the outlet to get it charged versus, oh, we've got to have a power grid change to get this at scale. So I think it's all a balancing act, and the secret is, where's the middle ground in all of these things. They're all going to be building blocks for the bigger and faster and better next thing, but it will provide a little bit more of, I'll go back to the crawl, walk, run scenario, to where maybe that's, if it's if they're operating, I'll just throw something out there, more rurally, well, maybe that helps us come up to speed on the airspace management. Those are the kind of things that might enable the ultimate of where everybody wants to be. That may actually be a faster path. That may not be a straight line. It may be, a big circle. And, if we all had crystal balls, that's where we would, what we would look towards. But I certainly think the path to profitability for some of these platforms could certainly be, I would say it would be less, a faster path to profitability would be a better way to say that.
Carey, I want to get your thoughts on defensibility. Obviously, aerospace is an industry with high barriers to entry. But if we're going back to our discussion earlier about OEMs sitting on the sidelines and waiting for the startups to de-risk the market, for the regulations to catch up before leaning in with engineering and certification and production muscle and capturing that market. That would be the case for the OEM. What is the case for the startup or a new innovator that's coming into this field and taking on all of that risk? How can those entities build defensibility into the end product?
I guess I would say, my opinion for the startups, and there's a lot of different directions they can go, but for me, I think the startups plan in my mind would be you don't have to do everything. You can get the technology or the platform to a point at which you're either partnering or you're selling the product to the next step. Because all of this is, there's a number of steps to get to a production platform. And in my mind, in the environment we're in today, we started out, I don't know how many companies we had in 2019, and that's when I was a lot more involved in, say, the eVTOL side of this. But it just seemed like every time I turned around, I was reading another headline of another platform, of another startup that's going to do this. And I'm being the engineer and knowing the piece of how neat it is for that group of engineers that are starting something new, developing another piece of technology. So that's the one hand, and the other hand, knowing how long it's going to take, and you don't want to stifle that, the that ability of, the sky's the limit often with these teams. Now, I will say some of them shouldn't have ever started, probably, but I give them an A for getting out there. But at the end of the day, not very many people are going to survive this, in the people moving part of electrification.
If you were to start your own company building an aircraft, a rotorcraft, what is the strategy that you would use to be able to compete with the big OEMs? Does it come down to doing things faster, cheaper, leveraging, perhaps some modern development tools? And I do want to get to that next. Or will it be, hey, let's develop something where we can grab some real technological moats so that later, even if the market de-risks and the regulatory pathway becomes, very clear, there's still distance between us and the rest of the world?
Yeah, I'll say for me personally, and having been around for a while, I would personally need to feel like the technology or configuration that I'm wanting to start up is a game changer. Because if I'm going to just change the number of rotors on on one of the current competitors, that's a failed start. So first, I think you have to at least feel like you have something that the rest of the world doesn't offer. And if you don't have that, and it's kind of harsh, but I just don't think you should get started. And quite frankly, the people that are, financing that and funding that, I think are going to be disappointed because one, it's a very competitive space and it's a highly technical space. And we talk about the tools, we've got great tools today, but guess what? They're expensive. So I would struggle, and like I said, this is my perspective. I would struggle today to say, hey, Canon Aerospace is going to open up and I've got a brand new platform that I'm going to just take over the market. That
That, by the way, is a great name, Cannon Aerospace. Where do you think that this next generation of game-changing technology might come from? Will it come from power plant, aerodynamics, materials, manufacturing, something else?
Well, I don't really think aerodynamics are sort of aerodynamics. I mean, I think there will be small tweaks that some of the new tools allow us to do to be more efficient, because that's really what you're talking about here is, can I be more aerodynamic efficient? I think the materials, there's a lot of, that's a very interesting area when you look at what additive manufacturing, for example, brings to the table. So I think additive manufacturing, material science, those are all going to continue to improve the platforms. along with the analytical tools. So I maybe I don't look far enough ahead because I've spent my career mostly working with whatever's available to create what's next. So I can't say that I know or would could put my finger on what's the next big piece of technology that's going to be the game changer for this. I know I would certainly like to say somebody is going to come up with a very clever power storage answer or very small hybrid, very high capacity. We haven't talked a lot about the hybrid technology, but I think that's in some of these areas that's the next step, and that helps solve some of the maybe help solve some of the problems that we see with a purely electric system.
Well, share for a minute what you see as the gaps in the small hybrid propulsion capabilities.
One, I just don't know that people have looked really hard at what we can do there. I know I certainly didn't put a lot of energy or thought into it, mainly because we were jumping straight to the all electric, at least most of the projects I was doing. But I think, as we look at what's the right solution for hybrid, one, you have to decide what's the size or weight range of the platform, and then look at, okay, what kind of hybrid propulsions can I come up with, and what does it give me? You know, it will require a lot of analysis to decide where's the happy medium for hybrid. How much of it's storage? How much of it's electricity or whatever generated from you know hydrogen, for example. And you look at hydrogen and you say, well, hydrogen, the big problem with it is I have to store it, and that has to be stored safely. So I think it appears to me that there's more thought being given to hybrid, but I certainly think that's an area that we could work on and maybe is a better next step to help solve some of the problems we have today with the shortcoming of power storage.
Do you think there's a lot of room for improvement in hybrid systems that are, let's say, in like the 10 to 20 kilowatt class that would be, small systems, but much more reliable than what's currently on the market and at acceptable level of fuel efficiency? Is that something that somebody just needs to go build since there's a new demand for it? Or is that something that people have been trying for a long time and it just still remains because of the physics of that type of a system? It just remains a challenge fundamentally.
Yeah, well, that's not an area that I've had a whole lot of focus and exposure to. I think at the end of the day, we probably need to take one step back and say, what are we trying to solve for? What does the size of a vehicle? If we go ahead and make the decision that, hey, this isn't a people carrying platform, I'm going to pick a payload, whatever, 200 pounds, then I think you have to start your analysis to say, okay, now I want a hybrid solution. You've got to start out with a mission and back down to what the hybrid solution is. And I do think there hasn't been a whole lot of thought or money put into the development of these hybrid systems. And like I said, I have very limited exposure, but I think if you could find the niche of I can power a platform of this size to do this job. I certainly think there's probably some room for the hybrid platforms to come in and say this is a good solution, but it's got to be like everything, safe and light.
Carey, let's briefly talk about the engineering tools that you have experienced firsthand. I think as we were discussing prior to the recording, you've arrived at Bell just as it transitioned from slide rules essentially to the first generation of computer aided design. Give us a sense of the evolution of these tools.
Yeah, so I didn't quite come in at the slide rule stage, but a lot of the engineers still had their slide rule in their desk. The calculators were available, but yeah, it's I look back and it's pretty amazing to me as I think through entering into Bell Helicopter for the first time and just seeing drafting tables as far as the eye could see. you couldn't have hardly found a computer in the building except for the mainframe that was running down in the basement. So you're talking about all of the designs being drawn on paper to when I joined, we had what was called CADM scopes, and the early ones had light pins. And it was one of the most frustrating things you ever did because if you used the light pen and you touched the screen and there was an intersection of 20 lines, you never knew which line it was going to grab. And to sit there and be frustrated with that was, it was just truly a frustrating deal. Fast forward a little bit, obviously all of that's in 2D. So you move from a CADM scope to something like CATIA or Unigraphics, where now it's the early days of that are still 2D, but there's a lot more capability and accuracy in the drawings. There starts to become at least an interest on how you can integrate that into, say, your manufacturing floor or something. You move toward from that to 3D. Now you're still talking about using a dedicated machine to do 3D design. It's not like, you know, laptops are coming on board, people are getting laptops on their desk, they don't have near enough power to drive these design tools. So you're still tied to these very dedicated, expensive machines to do 3D. You then transition from that to 3D with attributes. So you're not just drawing a wiring harness, for example. Within that wire, you're telling it where it gets connected. And so now you can start putting all these attributes with some of the things that are on the screen. Now that becomes a searchable database to where someone's not manually, building wire lists of one wire going to another wire. You fast forward a little bit more to that. Now that information is automated into the machine that's building wiring harnesses and links. In my early days, we'd build a wiring harness and we would roughly estimate how long the harness was going to be. Then we would have to make it single-ended and add some wire and then cut it off when we actually installed it to see how long it, where the other end needed to be. Now you've moved into a fidelity of 3D that you can, with confidence, build a wiring harness and have the connectors on both ends and understand that that is not going to be too long. Fast forward a little more, now you start utilizing some of the analytical tools of stress and ANSYS and CFD, and all of a sudden now all of these tools become interoperable. May not be the right word, but they can all help each other. And so the advancement in the tools that I've seen over 35, 40 years is amazing. And it's certainly, as a designer today who can basically have the entire model on their laptop in 3D and do analysis against it, can iterate. That's a whole lot different than, say, back in 1985, of having to get the vellum back out and an electric powered eraser and start erasing this stuff so that you can redraw. And my amazement is I look at the platforms that were produced before joining the industry, and it's amazing to me. You think about the Huey and some of those, they didn't have these tools. Now, they probably were not quite as efficient, from a stress. Some parts probably broke that shouldn't have, and other parts were over designed. So it's an interesting, I will say, thing to ponder when you look at where the tools have been, where they're at today, the capability that gives you, the simulation capability. And that's not only simulation of like how's the handling characteristics of a platform going to be, it's the crash simulation. You're not having to
Right.
sacrifice real airframes for, figuring out what needs to happen from a crash standpoint. What's going to happen with the landing gear, whether it's skid gear or wheels, and is it going to puncture a gas tank? I mean, it is amazing the tools that are available today.
What do you think is the end goal in terms of how these tools, especially AI powered tools, can shrink the development timeline? Let's say a clean sheet helicopter design that might take 10 years to develop using traditional tools. If you fast forward and imagine these multi-physics integrated engineering simulation tools, what's a realistic timeline for developing a clean sheet design?
So I think it obviously speeds up the timeline, but everybody has to understand that at the same time you're speeding up the timeline, you're getting more complex, or you want to get more complex. You want to put more capability in. So there's this, yes, I've sped up the basic design time for sizing a part, but oh, by the way, I want that part to do more than what I originally did. So it's counteracted a little bit because of when you become more efficient, you also, your desire is to be also become more capable. And I think so there's a little bit of a trade-off there. Now, I do believe that it is a paradigm shift, in my opinion, as we move into AI. I think the capabilities that gives you on the manufacturing side and simulation and all of those things, I'm not sure we comprehend the capability today. I know it's one of those areas that if you don't pay attention to, it it is amazing what happens in a matter of months right now in some of these areas of AI. Now, I will say for aviation, that's probably alarming to the regulators because they've got to try to figure out how to regulate it and how to certify it. And I'm talking about on the platform, not just the manufacturing. The manufacturing techniques, I think that's fantastic, and that's in use today and going to continue to grow. But I think as you start saying, I'm using some auto-generated code, I think that becomes very interesting as can the regulatory side of it keep up with the technology?
True. Well, we got to land this helicopter. So, any parting thoughts for the audience?
Well, for me, I certainly appreciate this opportunity. The vertical takeoff has obviously been a big part of my life, and it's been so satisfying. And I look back and look at where, the steps in technology that have transitioned over the past 30 years. And I think it's a really bright future for young engineers that are out there today. I think the sky's the limit. It's going to take pioneers in software and pioneers in cyber. We haven't really discussed the cyber side of things. That's a whole new engineering discipline that in the past people in aircraft hadn't really had to think about. And we could probably do a whole another podcast on just that alone. So I think the future is really bright for young engineers who are looking to get into aviation, especially vertical lift. And I'm sort of looking forward to standing on the sideline a little bit and watching what happens.
Well, thank you very much, Carey. We really enjoyed the conversation, and thanks for being our guest. And we look forward to doing it again at some point.
All right, thank you.
All right, that's a wrap for today. Thank you for listening to the Vertical Space Podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and/or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.